Okay, so just a quick question before we get started. Which of the following quantities can sometimes be negative? You've got potential energy, kinetic energy, and work done. Give yourself a few seconds to think, and then think about why. Okay, and then let's have a look. So potential energy, we remember is mgh. M is always positive. G, at least for our purposes, is always a positive number. It's equal to 9.81. And then H, this can be both positive or negative. So therefore, potential energy, PE, can be negative. Okay, so it makes sense to talk about a negative potential energy. Kinetic energy is defined as half times mass times velocity magnitude squared. Half is obviously positive, mass is positive. I'm pretty sure at some advanced physics level people start talking about negative masses, but I haven't understood that, and fortunately we won't be doing that in mechanics. But we'll take mass as positive. The magnitude of something and then also squaring it is definitely positive. So kinetic energy is always positive or zero, I suppose. Depends if you count zero as being a positive number. So you can never have negative kinetic energy, which in itself might be a constraint in some more difficult problems. And then work done can in fact be negative or not. Think about it. So you've got two approaches. You can either think about it as force times distance or change in kinetic energy. For both of those, you can get negative. If you've got change in kinetic energy, all you have to do is think of, well, if something speeds up, the change is positive. If something slows down, the change is negative. Alternatively, you could think of it as, well, work done is force times distance, or sometimes written as S, and both of these can sometimes be negative, right? Force can be a positive force or a negative force, because force is a vector. Or should we say it that way? I'm having slight doubts. Perhaps this should even itself be magnitude of force. But certainly, okay, for absolute sure though, we can say this one, right? Displacement, that can definitely be positive or negative. I suspect perhaps this force in the force times displacement, it might be a little bit like this velocity here, in that there's kind of an assumed magnitude that we're usually using, because ultimately we're talking about the force in the direction of motion. So then the direction of motion is itself going to the displacement. So it depends, I suppose it depends on your interpretation, but either way, indeed, work done can be negative. Okay, so the only one of those that has the restriction on its sign is kinetic energy. Okay, so this should be quite nice. We're deriving the result that work done is equivalent to change in kinetic energy. So remember, that was this statement. And we didn't prove it. And you know, with some things in terms of the universe, I suppose, it's not so much about proving it, it's more about observing it. But having some of the previous formulas that we've already got in terms of mechanics, we can actually prove this one. So for instance, F equals ma, as far as I know, that's not really a mathematical proof to get F equals ma, that's more like an observation. It's observed that this is a property of the universe. But if you take F equals ma and then couple it with another formula that we know about, and I'll give it to you, it's this one. So you remember V equals U squared plus 2AS. Right, so using these two, see if you can do it without cheating and just skipping to my solution. Can you think of a way of deriving, oh sorry, let me also just change this, I don't know why I wrote KE. Can you think of a way of deriving that the work done is equal to that, and all you need to do is use these two formulas, see how you get on. It's totally possible to do, so you can get the answer. Okay, hopefully you haven't just skipped and not tried it yourself. Let's see what it should be. So I'm going to start off with the things we've got in common, which are there's an A here and an acceleration A here, and I'm therefore going to rearrange this number 2 equation to make that A the subject, and then I'm going to substitute that into the number 1 equation. So we've got F equals m times v squared minus u squared all over 2s. So it's already starting to look a bit familiar. That is just then taking out the half to the outside, is this, still over s. And then if I multiply both sides by s, you get fs equals a half m v squared minus u squared, which of course is a half mv squared minus a half u squared. Beautiful, and it just comes out like that. And then of course F times S, that's work done. It's force times distance. So you've got the result. Hopefully you had some success in that yourself. Okay, and then we've got one example before going into some questions for you to try. And here we've got a parcel, mass 3 kilograms, pulled 10 meters up a plane, inclined at the angle theta to the horizontal, where tan theta equals 3/4. Let's draw that quick. So we've got theta, noting tan theta equals 3/4. If tan theta is 3/4, I can never remember this off by heart. Let's do the quick triangle. Opposite over adjacent. Okay, so therefore cos theta must be 4/5 and sine theta must be 3/5. Okay, no calculator needed. And then we're saying it's pulled 10 meters up, and the parcel's here, and it's got a mass of 3, and that's it, that's all the information. So assuming that the parcel moves up a line of greatest slope, sure, then we calculate the potential energy gained by the parcel. So potential energy gained, let's say when it started, let's keep things easy, let's say that's our 0 level, so that's where the potential energy is 0. What's the potential energy gained? All we need to consider is how high did it go. So what's that height? And that height will clearly be 10 times sine theta. We've just worked that out, is 3/5. So we get 6. And then I'm going to write a delta PE to say change in potential energy is going to be, in this case, mgh, which is mg6 or 6 mg. M is 3, so that's 18g. 18 times 9.8, which gives me 176.4 joules. That is the increase in potential energy. We know that because it's gained this potential energy, and this is something that'll come quite soon, is we'll talk about the fact that energy is constant in the universe. Whatever it is that pulls this parcel to, the 10 meter mark in terms of along the slope, whatever it is that caused that increase has itself now somehow lost some energy, whatever process that may be. If it was, a motor, then some electrical energy maybe was expended, or a battery was depleted slightly, or if it's a human pulling it up, then they themselves have lost some sort of energy in producing that increase in potential. So there's this transfer at all times. It hasn't come from nowhere. This object now sits there with this potential to do work, this potential to cause harm if you let go of it and it rolls down. And this is useful to know, and it's going to help us with quite a few calculations later. What I think I'm going to do is I'm going to extend this example. It's pretty basic, and I just want to add on sort of a bonus, I suppose. I want us to think about now, if I let go of this parcel, let's pretend it's not a parcel. Let's say it's a ball of mass 3 kilograms. So let's say it's a bowling ball, and then after having pulled it up these 10 meters up the slope, we're going to release it. And then what I'm interested in knowing is how fast is it going to be when it gets to the bottom of the slope. Okay, I'm just going to clear up a little bit of this this working first, but I still want to note that the potential energy at the top was 176.4 joules. So the first way we're going to do this, let's actually do it I guess let's do it the year 12 way for a moment. Assuming we don't have our new inside knowledge, or perhaps not necessarily new, but our inside knowledge about energy. We actually don't need to think about energy to solve this. We've got only a single force acting on this object, in this case mg, more specifically 3g, and if we break that into its parallel to slope and perpendicular to slope components, we end up with 3g times cos theta 4/5 here, and 3g times 3/5, which is sine theta there. So that's 9/5 g, and that comes to 17.64. Okay, so that's the force going down the slope. And then let's quickly use F equals ma, telling me that that's 17.64 divided by m, which is 3, should give me the acceleration, right? Which in this case is 5.88. Okay, so this bowling ball is accelerating at a rate of 5.88 meters per second squared down the slope. I've let it go, and that's how fast it's accelerating. So what we can now do is our suvat, right? We can say A is 5.88, U equals 0, the distance is 10, and the thing I was curious to know was how fast is it going to be going when it gets to the bottom of that slope. So that's V, and then T we don't include, I don't know about T. So we're going to use, I'm just hopping all over the board at the moment, but that's fine. So I'll say V squared equals U squared plus 2AS. V squared, I don't know. U is 0. And then we've got 2 times 5.8, 8 times 10. And that gives me 117.6, which means the velocity is going to be about 10.84 meters per second. Okay, so this bowling ball at that particular angle, left to roll at that particular distance from rest, will be going at a speed of 10.84 meters per second. So that's one way. That's using the suvat method. However, now let's be a bit more clever, because a lot of the working out we just did there was actually implicit in the derivation of the work done change in kinetic energy equivalence. So what did we say? Oh, I shouldn't have rubbed that out. It was about 10 point something. Okay. Well, we'll know again in a moment. So we didn't need to do any of that, really. I'll skip ahead. We've now got a shortcut to this. So potential energy, we said, was 176.4. When the bowling ball gets to the bottom, it'll be back to 0. So where has all that energy gone? It hasn't interacted with anything else, at least not in terms of hitting things. So that potential energy has been converted solely into kinetic energy. So what we're going to say is, right, effectively the change in kinetic energy is equal to 176.4, which was the potential energy it had. The only thing is, because it started in rest, it had 0 to begin with. So not only is the change 176.4, but the absolute value of kinetic energy at the bottom is 176.4. So then we can just very quickly say, all right, half mv squared equals 176.4. V squared equals 2 times 176.4 divided by 3 on the calculator. I get 117.6. Looks familiar. V is therefore equal to, 10.84. Yeah, that rings a bell. 10.84 meters per second. Right, much faster. And it's interesting, I find, because we didn't even have to consider about the angle. We didn't have to break the force of gravity into components. It just works. You know, it's quite beautiful, really. So we can start using this for all sorts of shortcuts, and that's actually what we'll be looking at, I think, in subsequent lessons, is how we make use of these energy properties to get really quick answers about how fast things are going, and you know how much time things took. Cool. All right, so that's that example done, and then time for you to really just try a few more questions yourself. Let's see how we get on with those. So it's 2 slides. These 3 questions, exam style ones, and then the next slide, I've just given you the challenge question from the textbook. Even so, perhaps you're okay with it. Do let me know if you feel like you need you know, something else to sort of sink your teeth into. But if you're happy with these questions, then that's good. You'll always have the homework as well. So these 3, give those a go, and then the challenge one on the next slide. I'll let you pause the video now. So this question, you're going to be showing a fundamental property of the universe again, kinetic energy and potential energy. The sum of them is constant, but can you show it in this particular case? Give it a go.